Good day everyone, my name is JB and today our group will explore the crucial role of mathematics in forestry through an insightful study on moth diversity in the Garbanga Reserve Forest, Assam, India. Mathematics isn't just about numbers. It helps us make sense of the natural world, and this study is a great example of that. Today, our chosen study is entitled An Analysis of Moth Diversity in Garbanga Reserve Forest, Basista, Assam, India. It is written by Golfina Ahmed, Arupna Madas, Lupamudra Bora, and Rizina Ahmed. The Garbanga Reserve Forest, covering approximately 117 kilometers squared, is a vital ecosystem bordering the Meghalaya foothills. However, urbanization from Guwahati City is threatening its biodiversity. This study focuses on assessing moth diversity in the forest, as moths are key pollinators and indicators of environmental health. By understanding how urbanization affects them, we gain insights into broader ecological changes. This study aims to catalog moth species and analyze their diversity, distribution, and population dynamics, assess the impact of urbanization, pollution, and human activities on biodiversity, highlight the ecological importance of moths, and advocate for conservation efforts. Essentially, the research not only helps us understand moth diversity, but also serves as a model for tackling biodiversity loss worldwide. Moths play a critical role as pollinators and prey in the ecosystem. Their diversity provides insight into the health of the forest. The findings could also guide environmental policies influencing conservation efforts. More importantly, the study supports the proposal to designate Garbanga Reserve Forest as Assam's 25th wildlife sanctuary, a step toward protecting its rich biodiversity. Now, let's talk numbers. The study recorded 140 moth species from 21 families and 126 genera. With a total of 2,882 individuals, the two most dominant families were Arabidae, 46 species or 33% of the total population, and Crambidae, 31 species or 22% of the total population. Interestingly, moth abundance peaked during summer, showing seasonal fluctuations. The biodiversity indices, including the Marjolef Index, which is 4.135, and Shannon Index, which is 2.30, indicate moderate to high diversity. This data proves that Garbanga Reserve Forest serves as a crucial refuge for moth species amid increasing urban pressures. This study spanned an entire year and used light traps with mercury vapor lamps to attract moths. These were set up from 7 p.m. to 2 a.m. in summer and 6 p.m. to 12 a.m. in winter, ensuring a controlled observation period. Trapping only occurred during new moon or crescent moon phases to minimize environmental interference. The detailed approach ensured that the results were both reliable and representative of the moth population in the forest. Like any study, this one has its limitations. Some key challenges included, number 1, lack of conservation strategies to mitigate habitat destruction. Number 2, short-term data collection, making it difficult to track long-term biodiversity trends. Number 3, taxonomic difficulties, as many moth species have similar features. And number 4, limited sampling scope, meaning some species may have been overlooked. Despite these challenges, the study provides a strong foundation for future research and conservation efforts.
Let us now proceed by understanding where and how the mathematics is used in the study. Mathematics plays a vital role in studying and understanding moth diversity. To begin, they tally the variety of moth species through simple counting. This provides the groundwork for further analysis. Next, they apply the Margalef's Richness Index, a formula designed to measure species richness and minimize bias. It is expressed as S-1 over ln times n, where S represents the total number of species, n is the total number of sampled individuals, and ln is the natural logarithm. The results from these calculations are categorized as follows. Values below 2.0 indicate low species richness, values between 2 and 3.0 suggest moderate richness, and values above 3.0 are considered high. Anything over 5 reflects exceptionally high richness. In this particular study, The richness score was 4.135. This result indicates high species richness, showcasing the impressive biodiversity within the ecosystem. Mathematical methods ensured that the study's findings were precise, unbiased, and meaningful. Raw data on moth species and population can often be overwhelming or prone to subjective interpretation. By applying the Margalip's Index, researchers transformed complex datasets into a single reliable measure of diversity. This approach not only allowed for a clear interpretation of the ecological balance within the Garbanga Reserve Forest, but also highlighted the extensive variety of moth species thriving in the area. Mathematics is a versatile tool that addresses diverse challenges in forestry and ecology. For instance, algorithms and spatial analysis process data from satellite imagery and aerial surveys, enabling researchers to map forest cover changes, monitor deforestation, and classify land use. These techniques are vital for tracking environmental changes and planning conservation strategies. Additionally, ecological niche models and machine learning techniques predict species distribution and habitat suitability, aiding species conservation and land use planning. Math also ensures that sustainable forest management by predicting tree and stand growth through growth equations and volume models. This helps estimate timber production while ensuring that harvesting aligns with ecological balance. From conserving biodiversity to managing resources, mathematics provides practical and efficient solutions that ensure the long-term health of ecosystems. Mathematics played a vital role in the field of forestry. It is the backbone of biodiversity studies, offering tools to uncover patterns and relationships in nature. Diversity indices like Margalef's, Shannon-Wiener, and Simpson's quantify species richness and abundance, helping researchers assess ecological health. Population dynamics models tracks changes over time, providing insights into how environmental factors influence species distributions and abundance. With spatial analysis, scientists can map species across habitats, identifying key conservation areas. Math also plays a predictive role modeling future biodiversity trends and analyzing human impacts like pollution and urbanization. These data driven approaches allow ecologists to transform observation into clear strategies for conservation. In the study of moth diversity in Garbanga Reserve, math wasn't just a tool. It was the key to understanding and safeguarding the intricate balance of the ecosystem.